Hello and welcome to yet another episode of That's Absurd. Please elaborate. I am part of your hosts. If this were a pie graph, I would be the delicious side. I'm Trace Dominguez.
Oh, okay. And what's the other half of the pie then? Huh?
I don't know.
The
That's
not
up to you.
taste, it's equally delicious.
Exactly.
The pie graph of how delicious the pie is like one half delicious and then the other half also delicious. And that's me.
Correct.
Julian Huguet, also delicious. This is what I'm going to have on my tombstone.
They're just different colors, but they're both delicious.
Julian Huguet, also delicious. I also love that you introduced it with yet another episode, like it's punishment. Like it just keeps happening.
And they just we're just going to keep showing up.
Yet another episode. No, make it stop.
If this is your first time joining us, this show, we talk to each other about questions that are sent in by you, the listeners. We answer those questions using our many years of combined science communication experience. We do the research. Occasionally, we call an expert, and they will actually talk to us, which we are eternally surprised by. And then we answer that question here on the show. Sometimes we have guests on. If you want to submit a question, go down into the show notes or go to our website. You'll find links. You can even call us on the phone, all sorts of things. And I just want you to know, we also have a Patreon, so if you want to vote on future questions, you can join and vote for those questions that may end up on the show. Very exciting.
Talk about, when you say experts will talk to us, that's, to me, still kind of shocking. And then the other thing that has been shocking lately is people signing up for our Patreon.
Yeah, it's really exciting.
They wanted yet more of us. They signed up for more audible torture. So we have to thank these people because, that's part of the perks, as we said that we would, along with being able to vote on questions that are submitted to actually help shape the show and what we answer. So we owe a big thank you to Summer Rain. Another one to Tessa Scott, Adam Foote, Kay Osawa, who, side note, I see what you did with your email there, Kay. That's very clever.
Yeah,
that's very nerdy
clever.
and clever, and I can't
it.
reveal it, but, nice. Ashley Silva, and finally, our very first patron who signed up day of. We're going to have to do something special for this guy, Alfonso Martinez. Thank you all so far for signing up for our Patreon and voting in the first poll. There's still, I think by the time this releases, there might be a little time to get in and vote on it. So if you want to be a part of this show as well, go ahead to patreon.com/that'sabsurdshow. Sign up for one of the paid tiers, and then you'll be able to vote and break. Because right now we have a two-way tie since we have an even number of people. Yeah, it's a two-way tie between the top two questions. So either you and I are going to have to break that and make somebody unhappy, or more listeners can actually chime in. Those are the two options.
Well, I hope it's the latter, but we'll be happy to do the former as well if we have to.
Yeah.
But either way, let's get into some questions that were sent in to us this week. And since I went first last week, Julian, I think you should go first this week.
Yes. My question was sent in by Josh, and I have a recording of it.
Oh, great.
Hi, my name is Josh B., and I'm from Philadelphia, Pennsylvania, although my family is originally from Ribeirão Preto, Brazil. So my absurd question is, how many tornadoes would it take to lift up a skyscraper? I sort of thought of this thinking about The Wizard of Oz from previous episodes. It's been a while since I've seen the movie, but I seem to remember the house being lifted and brought to Oz as well, which kind of had me thinking, tornadoes are real, and they exist, and they tear down buildings all the time, but how many would it take to just lift a really big one off the ground? Like, the Empire State Building or something. Thank you guys so much for your time. Bye.
Ciao. Obrigado.
Yes, obrigado. Awesome. The one Portuguese word I know. Josh, thank you. Thank you for listening. And I love when questions kind of cause a chain reaction and ping pong to a new goofy question. Yes. And this also dabbles in your apparent fandom for Wizard of Oz, which is hilarious how that keeps coming up.
I'm not mad about it.
No, but it is, relevant to Kansas tornadoes, The Wizard of Oz. Mm-hmm. So let's first start by talking about tornadoes. What they are, how they form, where they form, and what they can do. So a tornado is basically just like a funnel of wind. It's created when you have wind shear. So you've got wind at one level above the ground. So you've got some warm air traveling one direction. And then you go a little higher up and some cooler air is traveling another direction. And these two different winds, they circulate. They start to form like a little tube of air, but it's horizontal. So
Right. Magic.
yes, magic. Air's a fluid. It moves in fluid ways. It swirls.
You could call it night changes.
Why could I call it that?
Or maybe drag me. Or perhaps walking in the wind.
Are these album titles or nicknames for tornadoes I've never heard? What is this? What are we doing here? What's
These are
the
just
bit?
songs by One Direction.
Oh, okay. Well, I guess, yeah, tornadoes typically do spin in one direction, so that is fair.
Right. They don't know they're beautiful.
They're terrifying is what they are. So if you're into being terrified, yeah, sure, beautiful too. So the tornadoes, they start when you got this basically horizontal tube of circulating air forming. And then if a thunderstorm starts forming, what that does is the warm air underneath can start rising up, and it can actually tilt this swirling tube of air vertically. And it starts to kind of spiral toward the ground. You'll see like a funnel cloud is what it's called, coming from the bottom of these supercell thunderstorms. And if it actually touches down, then it is officially a tornado.
Yeah.
So the main places that tornadoes occur in the United States, which, by the way, is the place with the most tornadoes in the world.
Oh,
Yeah, fun fact.
I always wondered that.
Yeah, we have the most anywhere. And this place that gets the most out of all of the United States is Tornado Alley. So this is North Texas, Oklahoma, and Wizard of Oz fans, Kansas.
Kansas.
Right. So that's Wizard of Oz, accurate there. Good job.
Science.
Yes. So predominantly the reason it happens so much in this area, you've got warm air from the Gulf of Mexico coming up over Texas, meeting cool air coming down from northern latitudes up, near Canada. And it creates the conditions that in the springtime are ripe for a lot of tornadoes to form.
Are you saying that tornadoes are Canada's fault?
I am going to blame Canada for this one. And Mexico, the Gulf of Mexico.
They're all fighting.
They're teaming
we're
up
just
against
the battleground.
Curse you, other countries. This is a very American stance. Okay.
Yeah, it is.
So, and they typically form in the spring, right? April, May, June is when you get the most tornadoes. Now, tornadoes are categorized based on how intense they are with what's called the enhanced Fujita scale. Now, it used to just be the Fujita scale, and it goes from 0 to 5. And then in 2007, they updated it. But here's one thing I thought was really interesting. Yes, Trace.
You're telling me that the documentary Twister uses the incorrect Fujita scale.
Well,
the classic Fujita scale rather than Fujita enhanced.
The enhanced Fujita scale was introduced in 2007. So when Twister, the documentary, debuted in 1998, it was in fact still current.
Okay, but 96, in fact.
Okay.
Wow. Okay.
When the documentary
even older than I thought.
Okay. Anyway, by the way, of course, Twister has some cute references to the Wizard of Oz, right? Because they're trying to throw these like little balls into a tornado, and they call them
named Dorothy.
Dorothy, right? Which is based on a real experiment that storm chasers were trying to do, and they called that one Toto.
Oh,
isn't that cute?
Look at that, science influencing art, influencing more art, I guess, because then they made a sequel to the movie, and then maybe influencing science again. Who knows?
So the enhanced Fujita scale. What's interesting about tornadoes is, unlike hurricanes, it's actually really difficult to gauge how strong the tornado is before it hits, right? Like, hurricanes are classified, they're categorized based on the wind speed, but we can watch hurricanes form out over the ocean and build, and we can actually, measure their sustained wind speeds before they hit landfall, so we can prepare, like, this is going to be a category 3 or a category 5. Tornadoes are much more ephemeral. And that's part of the challenge with them. They form pretty quickly, and then they can disappear also really quickly. They can go away after a few minutes, a few seconds, maybe like in an extreme case, it can last for hours. But for the most part, it's like, all of a sudden, here comes a funnel cloud, it touches down, it rips through an area, and then it leaves again. So there's no real way to put like measuring instruments in its path or get a good measurement on radar, typically. So Ted Fujita was a scientist in the 70s who came up with the Fujita scale, and that used the damage left behind tornadoes after the fact to try and retroactively figure out how fast the wind was swirling around. So we updated that, like I said, in 2007, because it turned out that we were overestimating the wind speeds. And so scientists, engineers, meteorologists, they all kind of got together and said, okay, based on what we understand now, really what we were saying were 260 mile an hour winds. Those were probably like 200 mile an hour winds. So I can walk you through the Fujita scale. The problem, of course, is if something goes through an area where there is no damage. I don't know why that's a problem. That's a good thing. But for categorizing it, right, if there's no real measurable damage, we can't say how strong the winds were. So those are categorized as EFU, just unknown.
Interesting. The UFO of tornadoes.
Yes, the EFU is like yes, you got it. But then when they actually start hitting structures, we can start to quantify and estimate the wind speeds. So at the lowest level, when you've got minor damage, like well-built structures, those are fine. Maybe some broken windows, damage to roofs, chimneys, and big flat things like billboards, those could get knocked down. That's EF0. And that's wind speeds of 65 to 85 miles an hour or 105 to 137 kilometers per hour. This is going to be a conversion heavy episode. I'm sorry in advance. EF1, moderate damage. Mobile homes get damaged because they're not built structures that are anchored to the ground solidly. They're prefabricated. They get damaged more easily at EF1 with winds of 86 to 110 miles an hour or 138 to 177 kilometers per hour. You can also have vehicles that are pushed off the road or flipped over, but still, this is small potatoes we're talking about.
Right.
EF2, 111 to 135 miles an hour, 178 to 217 kilometers per hour. Considerable damage by these tornadoes. Well-built structures actually suffer serious damages. It can tear the roof off of them or collapse like exterior walls on more poorly built structures. Mobile homes just destroyed. They're wiped out. Yeah. Vehicles lifted off the ground. You got a lot of debris swirling around in the air causing damage. Yeah. EF3, severe damage, 136 to 165 miles an hour, 218 to 266 kph. Few parts of buildings are left standing. Well-built structures, all their outer and some inner walls come off. Unanchored homes, mobile homes, they're swept away, they're destroyed. Trains, train cars, those can be overturned. Small vehicles lifted up off the ground and thrown. EF4, now they're getting really violent. They're actually categorized as violent. 166 to 200 miles an hour, 267.
They could relocate your house fairly efficiently.
Yeah. Well-built homes, they're just turned to debris and rubble. Homes with no anchoring are swept completely away. Large, heavy vehicles, including airplanes, trains, large trucks, those can be flipped, pushed over. Yeah, trains.
Trains. Those are heavy.
Trains are quite heavy. Large trees can be snapped off or uprooted. Wow. Passenger cars picked up, flung very far. And then finally, at the highest level, EF5, that's 200 miles an hour and up, or 323 kilometers an hour plus. And that's just mind-boggling damage. Well built.
Hang on.
Yes.
That was a good-sized twister. What was that, an F3?
Solid F2.
See, now you've lost me again.
It's the Fujita scale. It measures the intensity of a tornado by how much it eats.
Eats?
Destroys.
Yes.
Just the movie Twister.
Yes, just occasionally insert some Twister clips in there. Thank you very much.
You're welcome.
Yeah.
I just watched it the other day. It's still great.
Awe-inspiring destruction. Just really, people who experience them are like, I was scared of nature. This was terrifying, right?
And only one person in this movie ever experienced an F5.
They are rare, and that is the good news. But yeah, they're incredibly strong. Doesn't matter if your home is well built or well anchored, it can be taken off the foundations and thrown airborne and then utterly torn apart. Cars, buses, airplanes, trains, large trucks, those can be rolled over or thrown through the air. Steel reinforced structures can be completely leveled. Ground's torn up, trees are snapped. It's real, real bad. On the plus side, they're rare. As far as we know, officially, going back to all the way to the 1700s, there have been 66 tornadoes that we have classified as either F5 or EF5. So
yeah, that's big.
Yeah,
but still 66 in what's that? 300
years.
I mean, that's not bad.
No.
That's not bad.
And
still more than I would have thought.
No, the last one was in 2013 in Oklahoma. in Moore, Oklahoma. And then in 2011, there's actually a glut of them. 2011 is kind of an insane year when you go and look at the records. There's a bunch, and a lot of them are in Oklahoma specifically.
Just to clarify, though, then, based on what you just told us, it's different mile per hour ratings, but it's also based on destruction. So it could just be the reason there was a glut is it just happened to hit populated areas more often that year.
Yes, that could be part of it. Because tornadoes are ephemeral and unpredictable and usually short-lived, there are myths about them. One of the major ones is that they just don't hit downtown areas, and there's like rumors, there's a heat bubble that drives it away or stuff like that. But the real reason is it's just unlikely. It's just a probability issue. The odds that
makes sense.
A tornado hits a downtown area is a small area. They're relatively speaking. And so
it's similar to like when people say, this meteor will hit the planet. And it's like, well, most of the planet's water. So it's probably going to hit water.
Yeah.
We can statistically say it's unlikely to hit land no matter what. But figuring out where, it'd be like, is it going to hit a downtown area? Is a meteor going to hit a city? Those are small spaces relative to everywhere.
So there's no special protection from a tornado being in a downtown area, and they have hit downtown areas in Texas, Oklahoma, and caused destruction. But again, EF5s are rare, and the chance of an EF5 hitting an area with a skyscraper also very rare, like even more so. That's not to say, though, that they haven't. There are examples of, say, an EF3 hitting a building. There was one, the Bank One Tower in Fort Worth, Texas in 2000 was hit by an EF3. This was a 35-story building. And it's insane looking because what you see is tons and tons of glass on the facade of the building is destroyed. 80% of the glass on this building is smashed. And that's not from the wind itself ripping panels off or the pressure smashing the wind. It's really that debris that it's carrying. So not to, harp on the Wizard of Oz for being unrealistic, but the idea that Dorothy's house would be picked up whole by a tornado and then deposited gently on top of an evil witch is just, I'm sorry to say it, it's not realistic. Especially older ones with older construction methods that weren't really made to withstand literally being picked up by a violent swirling windstorm. Once they're ripped off those foundations, those moorings, they just get shredded. They get turned into a tinderbox. When you look at destruction from EF3s, 4s, 5 that go through housed areas like that, it just looks like matchsticks everywhere. And that's flying around through the air while the storm is going on. So that is going to destroy a lot of the exteriors of other buildings.
I never thought about that, but the shrapnel kind of swirling around at those speeds is shotgun shell kind of stuff, like really awful.
And that is what is dangerous in a tornado. I mean, along with getting picked up and thrown around yourself, but the debris that's swirling around is what kills a lot of people. 70% of people are killed in the violent storms, the EF4s, EF5s, when we account for tornado fatalities. And, it's funny, there was actually a meteorologist who critiqued Twister in one of those Wired videos. Her name's Serena Arnold, and she critiques the scene where they just put some leather straps around like a pipe or whatever to hang on to something, and they're getting blown around. And she's like, they'd be smacked by debris and killed. Like that would be it for them.
Shredded.
Yeah. That's what you're really worried about in a tornado. So now let's talk about skyscrapers.
Yeah.
Because that's the other part of this equation, right? They are quite big. So tornadoes, obviously, they come in all sorts of different sizes, technically uncapped, but the fastest we've recorded is like 318 mile an hour winds, we think.
Oh, wow.
Yeah, so pretty fast when you consider that a hurricane category 5 is 150 mile an hour winds and up.
Right. And so 300 is like 500 kilometers per hour. So 150 is about half, 250 kilometers per hour.
Exactly. So tornadoes actually
fast.
can get really, really, really fast. But skyscrapers are the other half of this. And of course, if we're talking about skyscrapers, they're also all vastly different. You don't just copy and paste one design to the next. And there are some interesting instances of skyscraper engineering that was threatened by wind.
Stop it.
No, seriously.
Stop it.
Seriously. They are designed to withstand wind. As they get taller and taller, they get pushed on by those winds, and they're
all the time
designed to sway back and forth. That's part of what they take into account. Really, an issue for skyscrapers isn't so much the swaying, it's swaying so much that people inside get sick.
Yeah.
There was a skyscraper in Boston, John Hancock Tower, that when it was erected in the 70s, it swayed too much and people recorded feeling nauseated.
Ooh.
And then on top of that, the windows were not properly engineered. And so when it was hit with winds, and not terribly fast winds, like in the 50 mile an hour range, so like 80 kilometers an hour, the windows would come off and they'd tumble down the side of the building and they'd shatter other windows.
Oh, no.
Yeah, so
I was picturing like they rattled.
Yeah.
Because that would make me unsettled.
On windy days, the police would have to cordon off the street around the tower to make sure that nobody was hit by falling glass. It turned out part of the issue was the glass was not standing up well to the differential heating from like the cold exterior and the warm inside. So like it would pop out and fall on a windy day. Another wind issue came in the Windy City of Chicago, appropriately enough. In the 80s, the now Willis Tower, but then the Sears Tower, also had windows breaking from high winds.
Just falling out?
Just popping out. Yep.
Wow. Jeez.
But the one that I want to talk about the most, because I think it's actually a completely bananas story, is there is a building in New York City. It's the City Core Center. And it is, first of all, a really striking looking building, especially from the ground level. It's a 59...
I know the building you're talking about.
It's a 59-story skyscraper, and the bottom 9 stories are held up on stilts. These giant 9-story stilts. There's 4 of them, and they're not on the corners of the building. They're in like the middle of each facade.
Yeah, it's like it's on stilts, but it's like a quarter turn from where you would have put the stilts if you were a little kid building with Lego.
Yes, it's not how you would do it.
It's like a T, and on top of the T is the entire building, and there's a T on each side.
Yeah.
It's really messed up.
And
to
it
look
looks
at it.
bizarre, but part of the reason was the building was being built on land that was owned by St. Peter's Church, and they came to some agreement where it was like, okay, if you build it this way and we can kind of have a courtyard like underneath one corner of the tower, everybody will be happy. So it was engineering to overcome like a dispute over exactly who owned what and where to put this building. And so the engineer of the building, a guy who's Bill LeMessurier, won awards for it. And he came up with this really clever...
Somebody named Bill LeMessurier.
Yeah.
They have to work in this field. They have to.
LeMessurier twice, cut once. Once.
Do you think...
That would be my slogan. Although it's spelled totally different. It looks like Le Mesurier or something, but it's apparently just pronounced Bill LeMessurier. And he taught civics engineering at Harvard. And so he designs this building in the 70s. He came up with this innovative way of bracing the building against wind. He apparently came up with the idea at a Greek restaurant, sketched it out on a cocktail napkin. How all good ideas start, right?
Of course, yes.
And they build this thing. He engineers it. They build it. And then years later, he gets a phone call from a civil engineering student that says, hey, I don't think you accounted for everything. And he thinks, oh, that's cute. I'll kind of explain to you like what we did. And then he starts looking into what the student was concerned about. And that is wind coming at the building, not straight on to one of the square facades, but at a 45-degree angle.
So at the corner where there was no support, like at the T, at the edge of where 2 T-tops meet. Okay, got it.
But we're more worried, not so much the stilts, but the actual building above it and the way that it was braced against the wind was not designed to withstand that, because in New York City, it only had to pass certification for wind hitting it straight on.
On the face.
Right.
Yeah.
But this innovative way he came up with bracing it, it turns out when wind hits it at an angle, it was much, much weaker than if the wind had hit it straight on. So he's looking into it and he's like, but the way I drew it up, where the supports would be welded together, it should still be strong enough. It's fine. And then he discovers, while he's consulting for another building that's being built in Pittsburgh, and they're like, hey, the steel company that's erecting it tells him, look, it costs a lot of money to weld, right? Takes time. You need experts. It's much stronger than bolting it together, riveting it together. But, based on the tolerances and the calculations, right, it should be fine if we just bolt it. And he's I'll have to look into it. He calls up somebody and says, hey, on the City Core Center in New York when we did this. Would it have worked? And the guy he's calling up to double check with goes, "Oh, you didn't know? Well, the contractor, to save money, just bolted it instead of welding it. And we didn't run it by you because we figured it would be within tolerance."
Oh, no.
And so they had to retrofit. They had to go in and fix it and make it structurally sound enough to withstand if wind were to hit it at an angle. And they were doing it, by the way, when there was a hurricane that could have hit New York.
Oh, geez. Wow.
Oh, boy.
Wow.
Cool thing about the building, too, by the way, speaking of wind pushing stuff around and making occupants inside sick, it's got a gigantic 410-ton mass damper that's suspended in oil. And so when wind blows on it, this big lump of mass basically is tuned to literally dampen out the effects of the wind so it doesn't shift around so much.
Huh.
Yeah.
I did know that. That was the part that I'd heard on another incredible podcast, 99% Invisible.
Oh.
The mass damper that's one of those things where you're just like, I need to see it. I want to see it. I want to see it with my eyeballs. It's like, I want to go in the top of the Luxor Pyramid in Vegas. I want to go in there and I want to see all those bright lights and what they look like. And just, I don't know. I'm weird like that. I want to see all those things and the top of all the architectures.
Mm-hmm.
How they do this? How they make that?
How
make this?
How they do that? Yes. Yeah. So that was a clever innovation. And the point, though, that I'm getting at is that these buildings are engineered to withstand high winds. It's part of what comes with the territory. Now, so long as they're built correctly and engineered correctly.
Welded instead of bolted.
Yeah, depending on, so many complicated factors that are way above my knowledge, right? But there are tons and tons of engineering courses on statics and dynamics and how you have to take all these things into account and the different forces acting on the building. And ideally, if designed and built correctly, high winds shouldn't be a problem. But we're talking not necessarily EF5 force winds, but still high winds. So there's all these innovative ways that buildings get around it too. For example, the tallest building in the world is the Burj Khalifa that's in Dubai in the UAE. Mm-hmm. And when they were engineering this building, they determined at the top of the building, the major thing that they had to account for was wind. That was their biggest concern. And so they addressed this in a few different ways. If you look at the Burj Khalifa, it gets narrower and narrower and narrower as it goes up. So less and less of it is exposed to those strong winds the higher up you go. The corners are softened, which is a common thing you see in a lot of skyscrapers, or sometimes just like a corner cut out. If you ever look at even a very square skyscraper and you notice the corners kind of cut out around the outside, that is corner softening. And the idea is it helps keep vortexes from forming. So when wind is blowing at these tall structures, if you could see the air coming out the back of it, you would notice that a vortex forms on one side and then dissipates, and then a vortex forms on the other side. So it kind of would suck the building back and forth from side to side.
Right, yeah.
With corner softening, you reduce the formation of these vortices, so it doesn't get blown around as much. And then they actually decided to orient the entire building differently based on prevailing winds in the area. They just, when they were drawn up, they're like, you know what? If we just take it and rotate it a bit, so it's better for how the wind is hitting it, it'll be better.
Huh.
Yeah.
That's cool.
Yes. So it's designed to withstand gusts of up to 240 kilometers an hour.
Oh, okay. 150 miles an hour.
Exactly. Roughly. So that's, again, we're actually hitting EF3 territory. That's very strong winds up there. And it's made to withstand it. Other buildings, you'll see they have actual giant holes in them.
To like let wind through?
Yeah. The Kingdom Center in Saudi Arabia or the World Finance Center in Shanghai, they kind of look like the end of a seatbelt buckle. And that's just for allowing air to go through it. And sometimes designers even think like, oh, what if we put like wind turbines here, which hasn't really caught on. It's an interesting thought. And then one really interesting and extreme example is in New York City. There's 432 Park Ave, which is just the silliest looking Jenga tower I think you've ever seen. It just looks like a straight, tall, skinny rectangle.
Yeah.
And every 12 stories, there are 2 stories with just open space through it to let the wind go straight through.
Huh.
Yeah. And it's, again, just for reducing vortexes and the force of the wind on the building. So every building's different, and they all still take into account how much wind they expect to get where they are.
Right.
Now, Josh mentioned specifically the Empire State Building. The
Yes,
Empire
he
State
did.
Building is a much older building, right? It was erected in 1931. Can you believe it was built in 13 months?
You know what? Sometimes when I look at those old buildings and people tell me that, I'm just like, nah, I'm not that surprised, because part of the reason things take longer now is, safety regulations.
Yeah, there's that. The photos of the guys taking their lunch just sitting on a steel beam and be like, I don't know how OSHA would feel about this today.
Yeah, exactly. Yeah, how many people die in these skyscraper constructions then versus now?
It was also built during the Great Depression, and they employed thousands of people. It was a massive public works project.
And I'm sure they didn't have minimum wage laws that they had to deal with for that.
So the Empire State Building, when it was built, was the tallest building in the world for about 30 years. It's 443 meters tall, or 1,454 feet. That's to the tip of the spire, all the way up top of the antenna.
Yeah.
And in order to withstand the stronger winds as it gets taller, it also tapers down, kind of like a pencil.
Mhm.
And it's got a foundation that goes down 17 meters, 55 feet
Wow.
into the stone of Manhattan.
Wow.
Yeah.
That's chonky.
Yes, it's quite deep. And I mean, because it's an older building before modern materials and, computers that can help us design things, it's also just rife with these steel pillars and girders. It's
Totally overbuilt based on modern standards.
Yeah, it's very, very, very strong. In fact, in the 40s, it was actually hit by an airplane, like a medium bomber from World War II, smacked right into it, and people died. It wasn't great, but the building basically shrugged it off.
Yeah, the building was like,
thing.
Ooh, ouch.
Yeah. So again, this is another building where it's not designed to be hit by a EF5 tornado, but it is in a place that hurricanes do come through up on the Atlantic seaboard. So how much would it take to lift the Empire State Building? The thing is, I don't think it matters how many tornadoes you threw at the building itself.
Yeah.
Right? You're not going to uproot the Empire State Building.
55 feet, 17 meters of foundation sitting in bedrock.
Yeah.
Probably not going to be. Yeah, probably not.
And there's the weight of the building itself. Because of this older construction, right? There's a lot of steel, terracotta, brick, limestone facade. It weighs 365,000 tons.
Oh, that's a fair few tons.
That's
365,000.
That's a lot. Are we putting?
And those are the short tons.
The short tons.
That's 330,000 metric tons.
Right.
Sorry.
Whoa. Now, a semi truck is between 5 to 12 tons. That's empty to fully loaded. So at best, you'd need 30,000 fully loaded semi trucks to equal the weight of one Empire State Building.
Holy wow.
And yes, tornadoes are known for picking up trucks. But again, we talked about how even at the lowest level, like even at EF0, big flat-sided things like billboards get knocked over. Well, trucks are big flat-sided objects, right?
Yeah.
So they catch wind easily, and therefore they're more susceptible to being picked up by a tornado, even if they're heavy.
That's why I don't like driving next to big trucks on bridges.
No, I tell you something. I've rode a motorcycle on a long open stretch of highway next to big trucks, and when a gust of wind comes, I thought I was going to die.
Yeah.
I've ridden out to Joshua Tree where the wind was so strong I was basically riding in a straight line but tilted over to keep going forward. And yeah, when I go by a truck or a car, a big flat-sided SUV, it's a little worrisome. So if you were to lift up just the equivalent of the Empire State Building, I guess, that's kind of a more fair answer. Because you're not going to be able to actually uproot it.
Like, you snap your fingers and the building is somewhere, in the prairie of Kansas.
Yeah, just uprooted.
Just sitting there.
Maybe even disassembled, right? Because my thinking is, even if you could have, the building separated from its foundation, it's still really, really heavy. And a problem you're going to have is as the tornado swirls around, it's got all this debris in it and it smashes the windows. Much like that Park Avenue, New York apartment, you're probably going to open up passage for the wind, right?
Yeah.
So instead of being a broad, flat side, now it's permeable and the wind can actually travel through it, right?
And so then it would just get, the wind would get relatively weaker when it comes to the metric of lifting the building.
Yes.
Because the wind would just be able to move through the building and around the building more easily as the windows broke.
Right. You wouldn't want to be in those areas with the broken windows, right?
Yes.
A common myth about tornadoes is like, oh, you should go and hide like under a freeway overpass. And they've studied it and actually discovered that channeling through that narrow little gap can actually make the wind faster and more violent. And if you are under there with your little squishy body and you get thrown around into the concrete, that's bad. It would be better to go and find like a low ditch somewhere and lie down in the ditch.
And make yourself very flat so that you're hard to pick up.
So to kind of somehow get an answer for Josh's question, right? I thought, well, what if we made this kind of most ideal scenario?
Yeah.
Right.
What if we myth bust it?
We
can't blow this up, but we can blow it up.
We don't have the building anchored in its foundation. We don't even have it fully assembled. You just have like the raw materials that could become an Empire State Building, right?
Sure.
And so I started looking to, all right, well, what's the heaviest thing that I can find that a tornado has picked up?
Yeah.
And I found a instance in 2011 in Oklahoma where an oil rig was thrown by a tornado. Yeah.
What?
And
those are huge.
It's almost 1,000 short tons. It's like an 830 metric ton oil rig.
Wow.
With its drill going into the ground, providing some anchoring, and it was still picked up. Now, it probably is not ideal for withstanding the wind. I don't know exactly how they're engineered, but I imagine it's not a great structure if like a bunch of wind hits it really fast. Like there's nooks and crannies that can lift it up and carry it away. So again, there's some fuzziness. But yeah, an EF5 at one point, it's been documented, it picked up something that weighed close to 1,000 short tons. So if the Empire State Building weighs 365,000 short tons.
Oh, right. Yes, that's right.
If we're just going to do a 1-to-1, then I'd say you'd need 365 EF5 tornadoes.
Wow.
But that's, of course, like, I don't know how you quantify the total mass of debris picked up by an EF5, right? I'm talking about like one object here. Probably a lot more that gets picked up and swirled around per EF5. I don't know.
I think I know what that would be like.
Is there an F5? What would that be like?
The finger of God.
Nailed it. Now, the thing about the latest Twisters documentary that's come out is they actually have like multiple tornadoes as a plot point where they form simultaneously and then come together. And
spoiler, dude. Come on. Jeez.
Sorry. We haven't all seen it? We haven't all immediately run out to see?
Opening night, man. Opening night.
So good. Anyway, the thing about that is, first of all, multiple tornadoes happening simultaneously are unlikely. It does happen. Sometimes you see like a main tornado and then a smaller one like kind of nearby. But if they come together, in all likelihood, they're going to be spinning the same direction. So when they smash together, their winds are actually going to counteract each other, kind of like gears grinding together. And so they wouldn't amplify each other. In all likelihood, they would slow each other down and dissipate each other. So it couldn't be multiple tornadoes all at once. You'd need your pile of
Empire stuff.
Some assembly required Empire State Building.
You dump the set of Lego onto the table.
Long enough for wave after wave after wave of completely separate EF5s that, again, there's only been 66 in the last 300 years to come through and pick up all this material. So, if you are in a skyscraper in the unlikely event that a tornado is heading your way and you cannot get somewhere low underground, a tornado shelter, being picked up and whisked off to Oz would not be anywhere on my list of worries. Now, glass shattering and flying through the building, that would be high. I would be worried about that. I would find some internal area of the structure to try and protect yourself from
stairwell,
that,
or even under your desk if you're there working or something.
But yeah, whole building being picked up or even building collapse, right? Unless there's a unfortunate, like, oh, we bolted it because it's easier thing that nobody told the engineer about. Yeah, collapse, I wouldn't be worried about it either. Because again, the frames of modern skyscrapers are incredibly strong and wind is taken into account. There have been other buildings that there was one in Texas, another one that was bent and twisted a little bit. And then after years of examining it, they were like, actually, it's fine. And they patched up the exterior and sold the building and it's still standing today. So yeah, again, not my biggest fear. Oh, also doing this, it gives me a chance to talk about space stuff because I can't help myself. But have you ever thought about the vehicle assembly building in Florida?
Yeah, it's big. I've been in it. It's very big.
It's very big, right?
It's the largest one-story building in the world, as they like to say.
Correct. So it is 526 feet or 160 meters. It is technically the tallest single-story building in the world, right? Because it's just one big empty space, and they used it for building the different parts of the Saturn V, stacking them all up on top of each other, along with the crawler that the Saturn V, was wheeled out to the pad on.
Right.
And for all sorts of reasons, this had to be out in Florida. It's at Kennedy Space Center because, you want to launch a rocket in an eastern direction to take advantage of the Earth spinning that way to add a little energy to the rocket. You want to launch it over water. So if the rocket goes haywire, it doesn't land on people, houses, that sort of thing. And you want to launch it closer to the equator, again, because the Earth is spinning faster the closer to the equator you get. So this building had to be built with all of these engineering and logistics constraints. It had to be built out in Florida where there's a lot of hurricanes. And also, the ground is not great for building big, tall buildings.
How did they do this, Julian?
So you have essentially
thought about it.
A giant box kite. And so the secret is pillars.
They made it real heavy?
Yeah, well, they drove down pilings into the lime rock. And they go down. You thought the Empire State Building was well anchored. This thing has 4,225 pilings.
Oh, gosh.
And they go down 164 feet or 50 meters.
What?
Yes. Just so when a hurricane comes through Florida, it doesn't take off in the breeze.
They go down 164 feet, you said?
Yes, 164 feet, 50 meters.
Wow. That they go down a third of the height of the building.
Basically.
There's a third of the building underground.
Yeah.
Holding the rest of the building above the ground.
A quarter of the total building height, if you count from...
Julian, give me your best dinosaur roar.
Oh, God, an asteroid! It's horrible!
Wow, that was not where I expected that to go. We're popping in before the show to tell you about I Know Dino. It's a dinosaur podcast.
We think of those dinosaurs being this thing that's been dead for tens of millions of years. Even so, studying dinosaurs can still teach us stuff that is relevant to the world today.
Yeah, like climate models to help us understand global warming.
Migration patterns of dinosaur lineages, they tell us about Earth's changing continents.
We can also study dinosaur diets, what plants lived then and maybe what animals and how they interact.
And, this is super cool, many dinosaur injuries, paleopathologies, they're the first known occurrences of diseases.
And they talk about all this kind of stuff on I Know Dino. It comes out every week with new dinosaur stories that you're not going to hear anywhere else. Like, I hadn't heard of a lot of these, which is pretty cool.
You can find I Know Dino on Apple Podcasts, Spotify, wherever podcasts are. And if you found us, you can probably find them. Go check them out. From anchor to rooftop, basically a quarter of it is going into the ground. And again, there's over 4,000 of these drilled piled into the Florida swamp out there,
Wow.
Yep.
That's wild.
Yeah, cool. I love that fact about the VAB is an insane building. It's one.
It really is.
When they first built it, NASA wanted to show off just how big it is, like what an accomplishment it was. And because it's out there in the middle of flat Florida with nothing around it, you have no way of gauging how huge it is.
Like, really don't until you walk up to it.
Yeah, photographers from Life magazine were like, we specialize in photographing stuff like this. And they went out there and they came back to NASA and went, we couldn't do it. We couldn't just make the scale come across in photos.
The thing that gets it for me is when they repainted the flag on the building.
Yeah.
And they showed the painters next to the stars on the flag. Mm-hmm. And it was just like, they are teeny tiny in comparison to the star
Yeah.
And then they're like, okay, now show me the full building. And the star looks teeny tiny.
Yeah.
It's just like, it's so huge.
You could drive a bus down each stripe of the American flag. It's that big.
Wild.
Yep.
Super
Yep.
wild.
And people, I'm going to dispel a myth while we're here because I can. A lot of people think that it has its own weather inside, that clouds form high up and that it needs to be air conditioned as a result. And both those things are not true. The main whole structure of the building, not air conditioned, but clouds don't form anyway. So just going to put that to bed.
Thank you for putting that out there.
Yeah. I saw that. I was, because I was looking and doing my research on this and I saw it pop up in like a Reddit thread and people sharing it as, oh, fun fact. And I'm like, that's not true. Guys, it's not true. It's impressive enough on its own.
Yeah.
Anyway, but back to Josh's question. I hope that answers it to your satisfaction, Josh. And I also just want to give you a shout out. He said in his email to us that he's a chemistry student in his last year in college. And I just want to say, like, keep going, my man. Like, you got this.
You got it. Good luck.
We hope that you continue to find joy and passion in science and in your studies, and that it teaches you new and exciting things that you can then use to teach other people or improve the world in some way. And I don't know, I'm getting a little teary, but like when he included that in his response with his recording, I was like, I'm proud of you, man. I'm proud of you. So keep it up.
Oh, that was really good. Let's take a quick break. Julian can dry his eyes a little bit, and we'll come right back with another question about nuclear waste.
Yeah, buddy. Hello and welcome back to That's Absurd. Please elaborate. The first half of the podcast, I blew on and on about tornadoes and skyscrapers, and now it's time for me to simmer down and let Trace take the wheel. So Trace, what's your question this week?
This week, my question comes from Fred from Quebec. And Fred asks, would dropping atomic waste in a volcano be a viable solution? It's a very Roman-esque way to ask the question. If you remember Roman...
Oh, how could I forget?
That solve anything?
It's very in the vein of Roman.
Yeah.
Fred also out there in the wild ideas camp of problem solving.
Clearly, we have a question we prefer in some ways because this is ridiculous. Would dropping atomic waste in a volcano, that solve anything?
That solve anything? Would that be good for you?
Fred elaborates, with Iceland building trenches to try and control the flow of lava, I'm wondering how this natural phenomenon could be used for waste management and the betterment of humankind and the world. Fred, wow, bringing some high-mindedness to such a lowbrow podcast. Really proud of you. And I really like this question. I think it's really interesting, and it's a question that I think a lot of people have. Nuclear waste, scary thing for a lot of people. It's this, I was going to say black box, but it's really more of a yellow barrel. You see it a lot in media portrayed in a very specific way. Like, Julian, do you know what, other than nuclear fuel or like green glowing ooze, do you know what nuclear waste, like atomic waste is? What do you picture in your mind?
I mean, I have the benefit of first of all, being very interested in nuclear power.
Yeah.
And then on top of that, getting to just look up whatever weird questions in my head as a job, which is fortunate. So I think my knowledge is probably a little deeper than most, but still, I just picture, a lump of stuff, just like a little like mound of thing, not to get too technical.
Yeah.
That is scary.
Wow.
I think I nailed it. I think I brought my expertise.
Is that a haiku? It feels almost. No, it's not.
Okay.
So, yeah. In real life, atomic waste is not glowing green ooze inside of a yellow barrel that you would see in a Matt Groening cartoon. And instead, it's actually a much more complicated and nuanced idea, because atomic waste can be all sorts of different things. It can range from absolutely spent uranium fuel rods, which are actually just rods filled with tiny little hard pellets about the size of your pinky finger tip or like a thumbnail, and then all the way down to things like janitor uniforms that were used in a nuclear environment for long enough that they're no longer something that you would just want to throw out in the trash. But that usually is where they go, funnily enough. Like you would think, oh, this has worked in a nuclear environment, it shouldn't be thrown away. And it's no, that's still atomic waste. It's just not radioactive. It's not irradiated enough that it would matter. It's not going to be above background radiation. So let me break it down. Basically, atomic waste is categorized into 3 levels by nuclear regulators. There's low level, which is 90% of all atomic waste, and it doesn't need any shielding, and it doesn't generate any heat. So the stuff that actually the yellow barrels are that you picture, that's the janitor uniforms. That's wiping rags, mops, brooms, paper, protective suits, rubber gloves, just things that spend time in an irradiated environment. And so they have to track that and put it away somewhere. And usually it just goes out with regular trash once they've checked to make sure that it's safe. Because of the half-life of radiation, you just leave something there for long enough and eventually it's no longer radioactive. Sometimes long enough can be a long, long time, and sometimes it's only a few years. Then there's intermediate level waste. That's 7% of all volume of atomic waste. That needs a little bit of shielding, still doesn't generate any heat. So that's like tools, worn out parts from nuclear plants, plastics, chemical sludges, metal cladding from fuel reactors, stuff from decommissioned reactors. That's all intermediate level waste. And then there's high level waste. That requires shielding and also active cooling to keep it from melting or something like that. That's literally fission products, elements from nuclear reactor cores. And the most common there is uranium dioxide, UO2. And that's about 3% of all atomic waste. And so 97% of it requires almost no shielding and doesn't generate any heat at all. And is mostly just like parts and brooms and like paper. And all of these are disposed of in different ways. There are different waste streams. So the low-level stuff is stored at a plant until the radioactivity is safe, and it's basically equivalent to background radiation. And then sometimes it's incinerated. They literally burn it on the plant property somewhere, and that makes it so it's less volume of stuff. And then it might be stored in a low-level waste location if it needs to be, but generally speaking, it's joins the waste stream with everything else. Intermediate level, some is enclosed, which means maybe they'll put it in cement or something, or concrete, or bitumen, which is the sticky stuff they use to make asphalt for road construction. And so they'll kind of enclose it in that, and then they'll put it in a box or a barrel or something, and then store it somewhere. And then there's high level stuff, and this is the scary stuff that people are typically afraid of. And this is actually commonly stored on site at the nuclear power plant in a giant pool. Any of this highly radioactive stuff that needs active cooling, they just put it in a big pool of water. They have shelves and places to store it, and they can use a lot of space there just to keep it cool. The fuel that is in there can be reprocessed for other uses, sometimes stuff that isn't nuclear reactor use, but other still useful stuff. And after 40 years, the radioactivity of that used fuel has decreased to about 1/1000th of the level that it was when it came out of the reactor. So,
okay.
Yeah.
One thing that I do remember, in all seriousness, about looking into nuclear waste is that the amount, like the sheer volume of high-level waste is shockingly small.
Yes.
Right?
Yes. It is very, 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 very small. If you think about it in terms of just sheer volume of waste created and used. Let me see. I wrote this down somewhere. Here it is. In 2019, coal plants produce about a metric ton of carbon dioxide per megawatt hour. Meanwhile, one uranium fuel pellet creates as much energy as about 900 kilograms of coal.
Whoa.
Yeah. One fuel pellet, the size of your thumbnail, creates as much energy as 480 cubic meters of natural gas, or about 17,000 cubic feet, or 564 liters of oil, 150 gallons of oil, multiple barrels of oil.
Right.
So it's like, that's just one pellet.
Yeah.
The size of a thumbnail.
I'm quoting from memory here, but I remember something like the amount of high-level waste from creating enough energy for like a family of 4 for 40 years is like the volume of a cigarette lighter. Something like that. I wouldn't be surprised by that. That seems a little small, but I'm not an expert. It's just the amount of energy created from this stuff is so high relative to the waste streams of other plants. The sheer volume of coal required to make energy is ridiculous relative to the amount of energy from nuclear. People who might be thinking, well, those aren't really comparable, right? Yes, you're making electricity at the end of both, but the systems are completely different. Well, they're both mined. They're both minerals. They're both refined in some ways, although coal usually less. The thing is, they both actually do the exact same thing in the power plant. Right.
The purpose is coal is burned to boil water. The steam from the water turns a turbine. In a nuclear plant, the natural heating capacity of uranium heats water, which makes steam and turns a turbine. They're doing the same thing at the end of the day. It's just two different ways to do it. So I think it's important to remember that this low-level waste and this intermediate-level waste, this stuff that is essentially papers, brooms, mops, rags, uniforms, and maybe some metal cladding and some chemicals and things like that, that stuff is generally pretty safe not that long after it's retired from the plant. High-level waste is kept on site at the plant, and it's there. It's kept there safely. It doesn't go anywhere else until a long while later. And then where it usually goes is underground in deep geological burying areas, which we have in various states in the US and around the world. And it is still radioactive, but much less so. And they put it in a dry storage cask, which we'll come back to in a second. So that's the first thing we really need to understand before we're dropping stuff into volcanoes. But the second thing we need to understand to answer Fred from Quebec's question is volcanoes.
Right.
So volcanoes, they are openings in the Earth's crust. They are Earth's zits where lava comes to the surface and explodes. It makes Mars laugh at Earth sometimes, and then they just put if Earth was like Gen Z, they'd just put a giant sticker, star, or heart over
Mars
their
is
volcanoes.
not one to laugh. Mars has the biggest zit in the solar system, and it's an extinct volcano. Okay,
It's true.
I see
It's
you,
true.
Olympus
It's
Mons.
true.
You're not fooling anybody with that
point.
little dot that happens to match your red skin color.
Yeah, true. Good point.
Thank you.
So volcanoes are basically just openings in Earth's crust. Lava comes from deep in the crust, comes up into the surface. Molten rock is made of chemicals and minerals. So oxygen, silicon, aluminum, iron, magnesium, calcium, sodium, potassium, titanium, manganese, all sorts of different minerals, but also gases, little bits of rock are constantly ejecting out, and pressure and heat is pushing stuff all the time. The magma, by the way, that you hear the word magma, that's just lava that hasn't hit the surface yet. So under the ground magma, above the ground lava, similar to like asteroid, in space, meteor, in the atmosphere. It's just a different designation. But the reason it wants to come out is because there's a lot of pressure in the crust, a lot of pressure from all of the weight of all of that stuff on top of it. And also magma is lighter because it's hotter than the surrounding cool rock. So it's driven toward the Earth's surface, according to the US Geological Survey, which I thought was really cool, by buoyancy. So you can almost think of it as floating up to the surface because it's lighter, it's less dense than the rock around it, which is cool.
It's also, in many cases, and it depends where exactly, it might have some dissolved gases or vapor in it, like water vapor, and that causes it to come to the surface. And if the water vapor is still, if there's a lot of it as it gets near the surface, if it hasn't had time to like boil off because the magma's rising slowly, you get more explosive eruptions, right?
Yeah. More puffs, more pushes.
More big old like, and like shooting,
Belching
launching
and,
lava into the sky as opposed to like the gentle flowing down like Kilauea in Hawaii.
Yeah. Good point. Yes. And the USGS monitors 160 different active volcanoes in the United States, but worldwide there are 1,350 active volcanoes on the surface, and more of those in the oceans. 500 of those have erupted in the last century. So if we're going to drop nuclear waste into these, we have 160 active volcanoes in the US to pick from, and 500 that have erupted in the last century. I don't think you want to drop nuclear waste in a volcano that's going to erupt, though.
Yeah,
if you think
especially
about it,
if it's
you probably don't want
one
that.
of them explosive ones.
You don't want it to explode.
Don't
Not
want
a great
it. You don't
idea.
want to launch it. That's the opposite of what we're trying to accomplish here.
So there are three different types of volcanoes. There's shield, cinder cone, and composite. Shield, it looks like a shield, like a Captain America shield there, just on the ground. Fluid lava flows out of a vent or multiple vents and makes a big sloping dome. They can be several kilometers wide, so like a few miles. They can be hundreds of meters tall. So if you think Kilauea, like you mentioned, Mauna Loa or Mauna Kea, they're all shield volcanoes. Hawaii is known for that. There's the cinder cone volcano, which are small pieces of magma, kind of like coming out, and they harden, and then you end up with these little chunks. The magma cools really quickly once it's in the air, because if you think about being underground where it's hot, and all of a sudden it's only, 20 Celsius or 70 Fahrenheit, even though it's warm to us, for something like rock, not so warm. And then that breaks into pieces that are called bubbly pieces around the vent of the lava is coming out, and they accumulate, making giant piles. You see these in the United States in the Southwest. And then there's the composite volcano, also known as the stratovolcano. These are the most famous, majestic mountains in the world that were made by volcanic means. So Mount Shasta, Mount Hood, Mount St. Helens, Mount Rainier, Cotopaxi in South America, Fuji in Japan. These are all composite volcanoes. They're tall, they're even, they're steep, and they have repeating layers of lava flows, and they can be kilometers tall, thousands of meters. So that's all the different stuff you really need to know about volcanoes. But let's get to Fred's question. We've got nuclear waste. I'm going to assume we're probably only going to take the high-level waste. That's the stuff we're going to be worried about. If we're just throwing janitorial uniforms into the lava, like, okay, sure, yeah, throw them in there, whatever. I don't. It's littering. Don't do it. But, for the sake of this question,
right.
Yeah, why not? Mops, throw them in there, whatever. It's going to burn up. But let's imagine now we have to take this nuclear waste from a nuclear power plant somewhere in the world, and we have to get it to the Shield volcano. I'm thinking Shield volcano because it's easier to get up, right? You're not going to truck it up the side of Mount St. Helens or Mount Fuji.
I didn't sign up for hiking when I was transporting this high-level nuclear waste. That's where I draw the line.
Yeah. So if you're going to do that, you need
physical exertion. No, sirree.
No,
not
thank
for this
you.
Radioactive mule.
Okay, sidebar real quick. Have you heard of Type 2 fun?
No.
Have we talked about this concept?
Type 2 fun?
So Type 1 fun, everybody understands. It's just fun, right? You're out, you're having fun, you're doing fun stuff. I don't know, playing ping pong or going bowling or playing video games with your friends or just being social, whatever. Right. You're having fun, right? You're at a party, you're doing stuff. Type 2 fun is fun that's fun later, but not necessarily fun at the time. Like you go to gym with your friend and it's like at the time you're at the gym and that's not
miserable.
So fun. But then afterward, you're like, man, that camaraderie was nice, and it was good to have my friend.
Right.
There. Or, in your exact point right now, a long hike, which might not be that much fun. You wake up at 2 a.m. to catch the sunset on top of the mountain, and you're miserable, and it's cold, and you're hungry, and you want some coffee, and then you get to there, and you see the sunrise, and you're like, this is amazing, but I'm still so tired, and I have to hike back down, and I took my pictures. But then, a couple days later, you're with your friends or whatever again, and you're like, man, remember when we did that? That was so fun. But it wasn't fun at the time. That's type 2 fun. Yeah, I heard that concept, and I'm like, oh, perfect.
I like it.
Yes.
I like it. But I do think it is just a more specific term for when your body is tricking you into thinking that you had a good time because you're in so much pain and it needs to release endorphins and stuff. That's what it sounds like to me. I
never get those.
Childbirth sounds like type 2 fun in this case. Like, just saying.
Childbirth, type 2 fun. Maybe type 3 fun. Let's that one you convince yourself later that you're like, oh, it was beautiful and great.
Yeah. Was it?
Depends. I've never had to do it and never will. So somebody tell me. Type 2 fun, type 3 fun, type 1 fun? If you thought it was type 1 fun, I want to hear from you.
I don't think anybody's ever called childbirth type 1 fun before, but okay.
All right, so back to volcanoes and nuclear waste. So if you have a shield volcano somewhere in the world, and you need to be able to drive the nuclear waste to the top, nuclear waste is transported on trucks or on trains or on boats. And so we need a place where you can get the nuclear waste to the volcano to be able to chuck it in. Shield volcanoes, ideal for this because you can build a road up the side of it. And so shield volcanoes, common in Hawaii. So we're going to dispose some nuclear waste. May as well go to the beach.
Oh, yeah. The native people of Hawaii.
I'm sure they'll love it, right?
View these mountains as sacred.
Yep. The island paradise where 20% of the state's economy is tourism.
Yep.
Nuclear waste disposal location also.
So the Olympics, which by the time this episode comes out, the Olympics will probably have wrapped, but the surfing and sailing stuff is taking place over in Tahiti because it's French technically. And there are articles about how, it's also drawing attention, like the locals that were born there are trying to show like, hey, by the way, because France tested atomic bombs right next to us for 30 years, there's like really high incidence of cancer. Can we talk about that while there's all this global attention on us, please? Please.
Yeah. Wow. Yikes.
Just saying.
Thank you for bringing that up. No. Good point.
I just, again...
maybe
along
Hawaii.
With the logistical issue, like when we filled the Grand Canyon with water, it just feels so rampant of like, let's just destroy these cultural heritage sites some more again.
Solves one thing. Doesn't solve any of the unsolved other stuff.
Definitely going to be having to make up for that later. Hopefully.
This is clearly a perfect plan, Julian. No one is going to oppose this
Let's
perfect plan.
imagine we find a shield volcano. The natives hate it. Let's just say they're like, that thing... it sucks.
Mauna Crappa. This is Mauna
This is
Crappa.
the worst volcano I've ever put my village underneath. I hate
haunted, like the Grand Canyon. And
Fact number 7.
Fact number
this volcano
7.
is haunted.
So we have fuel used in nuclear power plant. It's stored in a pool on site at the plant called wet storage for 40 to 50 years. That makes it much less radioactive. And then they have to put that into something called an indestructible flask or cask. These casks are amazing. And I have a clip to show you.
Oh, okay.
So this is one of those flasks. Notice its size. This is a test of these flasks. What they're doing is they're actually going to...
They drop it, they hit it with a freight train, like...
They drop it, they hit it with a freight train, they hit it with a rocket. They do all of these things to make sure that it doesn't break. And then in this video, you can see it squirts just this little teeny out of it, and they're like, that's unacceptable.
Wow.
When they drop it off from like 100 feet. And they do all of this because they don't want any of this radioactivity coming out of these casks. They are super duper...
I imagine part of the freight train thinking is like, if we're transporting it via train to its final site and there's a derailment or something terrible, right? Like,
So the freight train is hitting it perpendicularly while it is mounted on the back of a truck.
So that like a truck that got stuck on a crossing. Got it.
Yes, it's all for like real world disaster scenarios. And the cask is just like, yeah, we're good.
I would love to be in that brainstorming session on like what else can we hit this thing with. I want to meet the guy who was
Aaron,
rocket.
you have your hand up? What do you want to...
What if we hit it with the strongest thing in the king's army, 10 horses?
Where is Aaron from all of a sudden?
Slowly shifting to Appalachia, as we covered in our episode with Ben Bolin. That's his real accent.
That's great. Yeah. I'm going to hit it with my three sticks.
The mightiest force known to man.
Known to me.
known to one man named Aaron. Which is me.
It's me. So he takes this high-level waste.
British peasant planning nuclear waste disposal.
You know what? You never know these days. So the U.S. builds more tubey-shaped ones. Europe builds more cubey-shaped ones. I like the tubey-shaped one for putting it into a volcano because, volcano, lava tube, tubey ones, So
natural fit.
We move the nuclear waste into this dry storage cask and we transport it to Nevada or Idaho if we're burying it. But, since we're putting it in a volcano now, we're moving it to Hawaii, to Mauna Krapa, and we're going to take it up the mountain with a big truck. The casks are made of 1/2 meter thick steel with lead and concrete linings. It's physically blocking, if you remember the episode that I wasn't in with Nora, physically blocking radioactive particles from getting out, since they are just chunks of atomic nuclei. So it's continuously monitored in this underground storage in Idaho and Nevada. That's a pretty darn solved problem. However, just like Roman, that solve anything? Sure, let's just start throwing it into a volcano, because why not? So we've got boats that currently move high-level waste. Any guess as how many exist in the whole world to do this?
Oh man!
I'll give you a hint. Single digit.
I'm at the risk of lowballing it and making the real answer feel unspectacular. I'm gonna just say 1. Is there? There's 5. Okay.
Yeah,
all right.
5.
Yeah. I mean, I can't imagine we're making that much high level waste and that it needs to get transported that often. So yeah, that makes sense.
Yeah. So we put it on one of these 5 boats. We take it to a truck in Hawaii to the shield volcano that we've invented for this answer. The volcano, let's say, is open. There's a lava pool, but it's not currently actively erupting. The thing is, of course, if it's not continuously heating the lava from underneath, then you get a solid rock lava plug on the top. So you'd have to break that. But let's assume somehow we have an Incredibles Bond villain-esque thing that we can just open and throw whatever we want inside. Okay? So a UK cask of high-level waste is 2,500 kilograms of nuclear fuel plus the cask itself, which is about 110,000 pounds. So you're looking at a very, very heavy piece of lead and steel. And the US ones are slightly different. So again, if we're using the tubey ones, they're a little lighter.
And then 2.5 metric tons of waste? Wow.
Yeah. And so it's like
a lot of waste.
They don't have to do this very often. It's a lot. So let's assume we have the tube-shaped one and we're going to throw it into the volcano. Regulations say the US tubey cask has to survive a 30-minute, all-engulfing fire that reaches 800 Celsius, or about 1,500 Fahrenheit. Magma, that is to say, lava that hasn't reached the surface yet, magma under the ground, 700 to 1,300 Celsius.
Oh, okay.
So
at the lower
it's gonna
end,
melt it.
Yeah.
Yeah, we could if the volcano was kind of cool, but otherwise it gonna melt open.
Yeah.
There's actually a really interesting, this is science communicators who are super into geology and volcanology hated The Lord of the Rings because if you haven't seen that movie, spoilers ahead, Gollum is, he falls off of a cliff into lava,
right?
A river of lava.
Right.
The thing about lava, in the movie, he sinks into it and the ring is in his hand, the one ring that they're trying to destroy,
right.
And it hits the lava and it sits there and then melts. Mm-hmm. Why did he sink? Lava is molten rock.
He'd have to be denser than the lava.
Boom. You have just nailed why I don't think this plan will work. It is a tube filled with things that are lighter than rock.
Even the lead.
Most magma has a density of about 90% of the equivalent of solid rock. It's really just squishy rocks.
Okay.
So steel is more dense than rock, so it should sink, not quickly enough for the cask to not be breached. So once the cask is breached, there's just radioactive material all over the top of the lava. Even though uranium is quite dense and some of the parts might sink into the rock, it's still kind of just a big mess. You've just created a nuclear incident because you've thrown it onto the top of something that will melt the cask, melt the stuff inside the cask, and sure, burn up the mops and brooms and stuff that you weren't in there with the high level waste anyway. But with the gases, bits of rock, ash, and ejection from the volcano, now all of that would be irradiated. So we've created a nuclear fallout scenario.
I think at the heart of Fred's question is an assumption that many people have about lava and volcanoes, and that is that it is an all-destroying thing, right?
And I think to add on to that it's basically like a liquid, more like a water than it is like a solid.
Right. There's that too. Although in an episode that will be upcoming with Alex Danis, I get into that a lot of whether lava is liquid or not. Spoilers ahead. But back to this point, though, that the common conception of lava, right, is we think of it as anything, no matter what, touches it, it melts and dissipates and is basically deconstructed and totally gone.
Right.
But I think the waste from nuclear fuel was probably already submitted to more intense conditions than lava.
Yeah, that's probably true.
It's getting bombarded by neutrons to the point where the atoms literally split apart, and that releases tremendous energy and heat, right? This is a major problem with nuclear reactors, is controlling that amount of heat to the point that it doesn't run away and melt through everything that you've built. But how hot is it in a nuclear reactor?
A liquid metal cooled reactor is 500 Celsius. A molten salt reactor is 860 Celsius. And a gas cooled reactor is 950 Celsius.
Right.
So all of these are cooler than what you would find in magma, except for the highest one, which is the low end of magma.
Right. But that's more for keeping, again, the core from melting down, right? Because if it gets hotter than those temperatures, it's not the uranium is destroyed fundamentally. It's the machine that's built to harness the energy cannot withstand those temperatures. But the elements themselves, they can get hotter than that,
Oh, yeah, absolutely.
And just have a runaway nuclear reaction and continue to break each other apart with neutrons and keep that chain reaction going. They're not destroyed and therefore rendered inert.
Yeah, I think that's a really good point. If you look at the Fukushima disaster, right? A runaway meltdown that happened in a place that was close enough that we could measure a lot of what was happening. When the Fukushima Daiichi plant was hit by a quake and the subsequent tsunami, temperatures inside the reactors, according to CNET, skyrocketed to 2,760 Celsius.
Whoa.
So 2,760 Celsius, about 5,000 Fahrenheit.
Way hotter.
The fuel rods were melted into puddles, and those puddles is what chewed through the floor, causing a big radioactive heap of debris and melt, and they just kept getting hotter and hotter.
Right.
And so if you think about magma relative to that, magma is relatively cool in comparison. We're talking, again, 7 to 1300 Celsius. So this is another 1300 Celsius on top of that, and you're still not quite there. That means if you throw it onto what is essentially squashy rock, what it will do is melt the cask that it's in, and the stuff inside the cask will just sit on top of what is, to it, quite cool.
Yes.
To use a Lord of the Rings phrase. So I just think that's very interesting. And so to answer Fred's question succinctly at this point, would dropping atomic waste in a volcano be a viable solution? The answer is no. It is not a viable solution because we kind of have this solved already. It does make people nervous because it has to sit there for so long to become no longer radioactive. I think another solution is to throw it into space and try and, get it
Oh,
to
yeah.
the
People
sun.
love that, right? What if we shot it into the sun?
You've seen rockets explode. They do explode. Would you prefer that we make the coast of Florida uninhabitable for 10,000 years or an old mine that no one is using in the middle of the desert unusable for potentially thousands of years? And thousands is even the long estimate, right? It is becoming less radioactive all the time. And so thousands in that the highest level waste is still quite damaging for humans if they were to open up all of this casks and get into it. But, let's hope that does not happen.
Yeah.
And I think we're also underestimating the future. If we're solving the problem of let's put it on a shelf somewhere until we can figure out what to do with it, and then in 1,000 years, we'll have figured out what to do with it. Like, have a positive outlook. That's my thought.
One of the big hindrances to nuclear power, right, is public perception. And
Yes.
this idea that nuclear waste is this scary, eternal thing, which, I mean, it is long lasting and it is scary. But it's kind of, it makes it in our minds like an overblown risk of nuclear power. And so, there have been previous plans on like where to deposit high level nuclear waste for a long period of time. And then when people who don't live anywhere remotely near it, because, it's supposed to be somewhere that nobody's remotely near, but like just in the same state, they're like, oh, well, we don't want it here. Right.
Yeah.
And it nixes the entire plan. And then you're left with these power plants that are just like, well, what do we do with this stuff? And it's just piling up on the premises. Right. But again, it's the amount of energy that it makes. It's still a tiny volume of stuff. I think.
Yes. I've got a stat for you from the World Nuclear Association. A 1,000 megawatt nuclear power station is pretty good. It would supply the needs of about 1 million people. So say Seattle would produce about 3 cubic meters of high level waste in a year. 3 cubic meters. So
small.
That is about the size of 4 hot tubs. That's it. For a year to power 1 million people, right? So if you think about that relative to nuclear waste that you think in your mind, like that's not that much waste, relatively. About 4 hot tubs worth for 1 million people for a year. And that's all the waste. Like that's all the high level waste, everything.
And the low level waste and all that stuff, is that included in that
that's
figure?
just the high level
waste. Okay.
Yeah.
Yeah, it's for volume, for the bang for your buck, it's very, very small, right? And nuclear power is kind of coming back into vogue. There's a lot of difficulties with building a nuclear power plant because you have to find a suitable place with water, and then there's the public perception that you have to like reassure people, and the investment in setting up a generator. And it's finally starting to kind of come back into the picture with our worries about climate change. Construction's just started on a new molten salt reactor like demonstrator out in Wyoming.
Yeah, there's a new one. It's like the first new nuclear power plant construction in 50 years or something.
Yeah,
it's
in the United States.
It is coming. It is in the U.S. It is coming back. We are very scared of it. And I'm not saying we shouldn't be. I'm not saying we should. I'm not going to tell you how to feel about it. But I am going to ask that you know what you're feeling first. You know why you're feeling afraid, as opposed to just being afraid. You could be afraid of the dark, but once you know what's in the room, it's less scary. And so let's turn the lights on. Like, let's look at nuclear power with a little more of a discerning eye rather than just pretending it's scary and there's nothing to be learned from it and walk away. I want to wrap up my answer for Fred by saying nuclear power is a green energy in many ways, it's got to be a co-solution to climate change. It has to be. We've got wind, we've got solar, we've got hydro, we've got advanced batteries that can go on the grid for energy storage. Nuclear has to be part of the equation. And all of those things together, we have low emission power generation with very minimal waste produced. Like imagine if every ton of CO2 that we're putting into the atmosphere, imagine if that was a solid block, right? You would be very upset with the amount of waste we're generating. Now imagine we got rid of all of that, and instead for every million people, it was 4 hot tubs worth. And it was a solid piece that we could just go put in a place underground where we know where it is. We're monitoring it constantly, and it's just there, doing exactly what we hope and expect it to do. Nothing is without side effects and risk, obviously, but we shouldn't be afraid of it just because we have been.
Yeah.
Let's try it.
It sounds scary, and it is to be respected, but not necessarily feared, I would say.
Yeah. Like Julian.
Nobody respects me. What are you talking about? I also love that Fred is like, well, they're, in Iceland, they've got all these volcanoes, and it's like Iceland also happens to be this one kind of Goldilocks place where you've got like seafloor spreading right underneath it and like hot spots bubbling up, so you can actually put like geothermal energy. The one lucky place in the world, because that's another common question, right? If Iceland's doing it, why don't we? And it's because Iceland won the geothermal energy lottery if you were going to do it anywhere,
Yeah, exactly.
But again, you can't just throw all your problems in the volcano, okay?
You can't just throw all your problems in the volcano. You can't do it.
It's sometimes you got to come up with a real plan. You can't.
Yeah. I actually think the cooler part of the whole plan, the thing that I find the most fascinating, isn't even the storage part, it's the language part. English is only like a few centuries old, really,
right?
The English we're using. So what do we do in 1,000 years? What language are we going to be speaking? What signage do we put onto nuclear waste disposal places, like high-level waste storage areas? What do we put on there so that a future person knows that it's scary and knows that that is radioactive and knows that they shouldn't open up this giant cask filled with lead and cement?
I know there's some good stuff in there. If I can
There's
just
gotta
get
be.
at
They kept it so tight. There must be gold in it.
Yeah,
and it's just
you
like,
think I'd leave my gold at the bottom of an abandoned mine encased in steel and lead where anybody can find it?
Yeah,
you don't know me at all. To paraphrase Ron Swanson.
So that, I think, is a very cool problem. It reminds me of the 100-Year Starship Project, where you're like thinking about things that haven't yet happened and that we're not sure how we're going to solve. But it comes back to my same point, which is we should trust in the future people, right? We need to make energy now. Let's do it with less waste than what we're doing now, damaging the environment in a less and more controlled way. And then in the future, those future people, we will work with them to try and solve it. Have positivity for the future. Don't think that the future people are stupider than us.
Yeah.
Let's hope they're smarter.
We're the dumb ones. We're going to the people looking back 100 years from now. They're going to be like, can you believe they thought that everything was going to be Chernobyl?
Yeah. Yeah.
Maybe.
You never know.
I don't know.
You never know. So, Fred, thanks for your question. Would dropping atomic waste in a volcano be a viable solution? Not more viable than the solutions we already have. And, sending it to the sun? Nah, not really either. Also, Diana Physics Girl once told me in an interview when we were talking about something, she said, you can't really get to the sun anyway.
Oh.
Because of momentum. If you were to fire a rocket toward the sun, the closer you get, the faster it's moving around the sun, and you'd have to overcome that to get closer and closer and closer to the sun. So you're probably never going to get to the sun.
Orbital mechanics is such a pain.
I was like, wow, blowing my mind right now that Superman really just polluted some orbit closer to the sun with all of that nuclear material. What a jerk.
Oh, we could have second glowing moon, though. Okay, we don't need to spitball on that. It'd be cool, though. Glow moon.
I mean, second glowing moon would be pretty cool.
Ooh. All right, well, that is going to do it for this episode of That's Absurd. Please elaborate. The show was created, written, produced by me, Julian Huguet.
And me, Trace Dominguez.
It was also produced and edited by the wonderful and positively glowing Kyle Sisk.
Special thanks to the listeners who submitted questions featured in this episode, Fred and Josh. If you want to submit a question, look for the form down in the show notes. You can email us at hello@that'sabsurdshow.com. Visit our website, that'sabsurdshow.com/ask, or even call us and leave a voicemail at 302 tape show. If you want to vote on questions that we would potentially cover here on the show, make sure you join our Patreon. You can find out how to do that down in the show notes as well, but just go to patreon.com/that'sabsurdshow.
If you want to leave us a review wherever you're listening, be that stars or hearts or typed out words about your feelings, it helps people find the show. And, we read them. We actually read them. It lets us know how we're doing and makes us feel good when they're nice. Which they
when they're nice.
almost always are. But again, it doesn't have to be. I don't want to pressure you. You do you. You be honest with your feelings. Don't let me influence you. And a special thanks to those listening on Nebula. Nebula listeners get access to ad-free versions of episodes, and they support us and other independent creators. There are a lot of great ones on Nebula. I'm finding more all the time. I just found City Nerd, I think it is. He's great and hilarious and deadpan, and I like him a lot. So if you want to support us and other independent creators, go to Nebula. That's go.nebula.tv/that'sabsurdshow to sign up using our link.
Remember, Julian, we should remind ourselves to come up with a catchphrase to say at the end of every episode.
You can't throw all your problems in the volcano. Lava can't melt all your problems.